Thanks to all the CanBIM guys having me up here. I started a company last year while teaching BIM in college. And so I basically built a company on a concept, an integration concept. And I think only you guys can probably really understand what this really is that, I solved the GBXML import-export using energy analysis software. And I've been perfecting it ever since. And it's kind of, that integration has created a business and has taken on a life of its own. So I'm just here to share some of the experiences with you guys. I've moved out to Edmonton out west just to kind of keep up with the capacity. So it's, I've been having lots of fun with it, but it's very, comes down to a theoretical art. So where we are now, there's a lot of energy modeling software. I know David touched upon it. And that's part of the problem. There's too much software, there's too much technology. What do you use? What should you use? How should you use it? So there's a lot of stuff out there. But I think where we could be with energy modeling software is we can get further and further with integration. And I know the guys at D&D at John Hale, they were talking about it. And so there's a lot to come, but we're still not there yet. And so it's still all a big work in progress. But I see a lot of hope. There's a lot of optimism, and where we're heading is kind of the world of, my internal world is changing a lot more abstract. I'm doing pattern recognition. I'm finding trends inside buildings. I'm reducing energy through patterns, and I'm changing the patterns, and I'm comparing these, this data versus other data. So the world is changing very quickly, and it's getting very, very interesting once you're kind of on this BIM concept, which basically facilitates this whole process. So I like to start off with this common graph. I think most of you have probably seen it before. I tweaked it just a little bit. So this is a graph comparing to the non-farm productivity. So we're comparing the construction industry to basically Google and Yahoo and Amazon. And why are they so efficient and why are they so productive? And where are we and where are we going? So I think I had to change this graph because I think you guys can probably understand that the BIM efficiency actually sets us up a little bit higher than the traditional approach. So I think we can all agree that we are all getting more efficient at what we do. And I've seen some of these benefits myself. My process is getting more efficient, and I'm even projecting myself to be even more efficient. So the whole process is getting easier. It's all changing. And now as this kind of data world is getting more and more rich, we can get more efficient at doing what we do. And, and I think part of this is that, if you compare this to a sports team or a soccer team, whenever you're playing with pickup players, you're never going to win the championship. But if everyone's playing on the same team and we're all playing in the same league, we're all going to get very competitive and very efficient. So we all just got to start playing by the same rules, because if I'm constantly converting CAD drawings and PDF drawings, it's always going to take me longer to do it. But if we start working all together within Revit models or within BIM models, then it's all kind of a common language, and we can all do a better job and start working more efficiently. So I come from, I guess, the green building sector. So this is my focus as an energy modeler. I'm targeting energy, and I'm trying to see how I can conserve energy. So that's my prime role. And I find that this graph, again, is a very kind of textbook graph, is the integrated design process. So the top line is the ability to impact cost, and the red one is the cost of design change. And part of the problem is that I'm coming in about halfway where that blue line bends in. And so where I come in to do energy analysis is there's no way I can change any sort of function. It's very hard to change any sort of design because it's too far in. There's too much to do, and it's not worth it anymore. But that's just because you called me too late. So, and this is where I see the opportunity with the integrated design process, and that itself has a lot of adoption barriers. But I feel that this process of getting design charrettes, getting people together early on, is an area where we can find a lot of opportunity. And if we can get guys, energy modelers, to come and produce a lot more data that you can use to naturally ventilate your building or passively heat or bring daylight to 80% of your spaces. It's something that we can do only if we're brought in early. You know, it's really, really hard to tell an architect to restart or do it all over. We need to start a lot earlier. So here I've got the energy conservation measures, and I blanked them out. This is a case study done for 50 net zero buildings in North America, primarily the States. And there's all these energy conservation measures. And now, to me, an energy conservation measure, as an energy modeler, is everything that's above a baseline model. So when I do an energy analysis, I have to always compare to ASHRAE 90.1. I have to do a baseline model, and I have to compare to it. So if you're comparing the same thing over itself, then it doesn't really count. And if it doesn't count, you can't get incentives, and it doesn't count as a lead point, whatever it is. So this is where I kind of use it to compare. But we've got lots of things that we can apply to buildings. We got ground source heat pumps, underfloor distribution, heat recovery, high performance HVACs, natural ventilation, high R values, building envelopes, high efficiency lighting, and daylighting. Daylighting was actually the #1 feature that you can put in a building. And it's actually, I mean, these are common things. These are everyone's common sense. But when you're 50% done your design, it's really, really hard to work daylighting in. But it's the easiest thing. It generates the most amount of value. You can reduce the size of your mechanical system. You can optimize performance. So, I mean, there's tons and tons of benefits you can do. But you have to kind of start these goals on early on and just kind of work them in as you go, because it's a lot easier designing a solution than dealing with a problem. So I'm always faced with these problems, and I got to find solutions for them. But if they never existed because we designed the building properly to start, then it would be much easier. So here's a modified project life cycle. So this is the life cycle that I go through. And I've actually broken it to in 3 stages. It starts off with the conceptual design, which half the time I'm not even there. And so it's something that, as a compliance, and I mean internally, I need to figure out my own workflow and how many times I'm going to do these checks. How much work am I going to put in? So the conceptual design is an area where you can measure a lot of preliminary data, but realistically things start at schematic design. We can do program analysis. We can see how much energy you're going to use. So we can predict a lot. I mean, at that point, we can maybe get down to 25%, 20 if the amount of work we put in. So they're still kind of predictions, but they're kind of puts you in the ballpark. It starts to size your system. We can start producing loads, optimized loads for that is. And then as you get the loads in, this is when we can start designing these systems. And then we got design development. So we start to keep a track through design monitoring, see where your systems are, see how they're performing. And then finally, there's the construction documents where I have to basically do compliance reports. You know, I need 100% documents to do a compliance report. But this is where I'm a very theoretical guy. So I wanted to create the perfect energy model, the perfect process. And this is where I see there's a lot more, because I'm predicting the energy and I'm saying, okay, I'll probably be 10% accurate, or I'll know how well I can tune a model. But they're only predictions. And so when we get operations and maintenance, they could be off by a little bit, and that's fine. But I think the next step that I start to take is to calibration, model calibration. So I'm working a lot with existing buildings right now, where that's all it is. I'm dealing with existing operations. And what I'm doing is a little funky graphic created. The green line at the top is the energy model. Say it's an energy model prediction. The squiggly little black line is the actual operations for a building. So it might be off by a little bit, that's fine. But what we can then do is the calibrated model is that we can start to tune your building using what's actually happening versus what I predicted happened. And then we can start to learn and we can start to re-optimize. And at that point, it's, I mean, it's the whole building, the whole life cycle of the building needs to have this whole control of how your building's using energy. And if you want to change its patterns, if you want to change occupancy profiles, or if something else happens that I couldn't predict, if there's a higher heat load going on in the workshop that I wasn't ever aware of, it's something that I can re-account for that recapture that energy and send it back to heat recovery. So there's a lot of really neat things that you can do, and this is the concept that we use for existing buildings. So I'm sure most of you probably seen this chart. Again, this is what I used to teach Revit in school. So this is the theoretical BIM. And starting my company, I basically wanted to create a business that latched on to this process. And I knew I wasn't going to understand the whole thing. And I knew, 90% of the work involved is other people's work. It's other consultants. But I figure in a theoretical world, if everyone plays by these rules, then we can all start to work together. So I'm assuming everyone plays by these rules. And what I've done is I've integrated myself into this process, the process where I think most of you all kind of work and live in. So if we can all work within the same workflow and we can all exchange information in the same language, then we can all start to, I guess, coordinate information this way. And I basically broke down my process into 6 steps, right? I coordinate information. And as an energy modeler, the biggest job that I have is project management. It's not my job. It's gathering information, coordinating information about lights, HVAC, systems, envelopes, you name it, I got to go through it all. So I coordinate it. I create databases, and these are databases built in Revit. And this is the data I can start to output. I can collect it. I can organize it. It's all there. Everyone can see it. It allows me to validate my designs. It validates my energy models, because sometimes I'm working either side by side with mechanical engineers or working with architects, and they're kind of a different party. So it's something that I can now validate. Is this your design intent? This is what I input in my models. Now I'm sharing that with you. And so once I get this validation, I start to simulate. And I simulate this data. I create lots and lots of data, and then I start to analyze it. So I see all these nice charts. I start to pick up trends. But the last part was, and that's part of the problem with energy modeling software, is that it's disconnected from BIM up until now. And up to now, I've been, energy modeling is you're that guy in the corner working on a laptop, and no one's ever going to talk to you. And at the end of the day, this guy in the corner spits out a report that's 120 pages long that just goes and sits on somebody's desk or gets approved by compliance. So I thought, that's not good enough. I want to actually make a change. And so part of it was to communicate. So how do I communicate the thousands of lines of data that I've now produced, and how do I put that in a way that you guys can understand? You guys are the other consultants that I would work with. And normally you would have hundreds of people working on a project, and I'm kind of holding more information than I can even handle, information that's kind of spewing outwards. So what I started doing is actually putting the information back into the BIM models, because the analytical software I use is analytical. It's not meant to communicate. It's not meant to share. It's just it's good at what it does. But then working with the 2 softwares, and that's where my job gets really complicated, so I work with a lot of software. And so I started putting this data back in, and I started sharing it. And at every life cycle, at every process, your model, the one that I share with you, gets richer and richer and richer in information. And you can then go to this room and see how much heat gain, heat load, power factors, all the information you would want to make a decision to size your system, to design your building. If you start to change performance, you get the information and I get it as well. And so it's kind of an information workflow that I'm working with. So, and it starts off at the conceptual design. So this is a case study for a building in China. I haven't worked on this, but I just thought it was really cool. It's a LEED Platinum building. They worked in everything that they possibly could, but this stuff needs to start to happen early on. If you want to do rainwater collection, natural ventilation, you got 80% of these spaces are daylit. And this reduces enormous amounts of load. But you need to start to measure it, and you need to start earlier. So the energy modeling concept, it's a common concept. I think there's must be 7 or 8 softwares out there. But there's very few that have integration. There's even less that can even do dynamic simulations. So it's basically a computer program that helps clients optimize their design and prioritize their capital viability. So if you want to save energy, to save money, you got to reinvest some of that, and you want to make sure that it's the best bang for your buck. If you want to put triple pane glass, great, it's going to cost you, but how much is it going to save you? And that's what the point of energy modeling is. So here I've got, I mean, it's a big audience. I've got a little 8 modules, 8 little individual modules, and the windows on those are exactly the same area on all the windows. And if how I learned engineering is that a typical heat loss calculation is a simple formula using area, an area calculation. But here, I'll tell you the answer. One of these modules performs worse because of infiltration. So even though you have the same amount of window area, it doesn't count anymore. The old-fashioned calculations don't work because you have a higher perimeter of window. The more perimeter, the more cracks. The more cracks, the more infiltration. The more infiltration, the higher the heat loss. So it's getting really, really dynamic in a way that we can't do this job manually anymore. You know, it's getting very, very complex, and it's something that I can account for, and the engineers can account for, and we can start to work together. So some of the existing buildings, I have to put a higher infiltration rate to be able to calibrate the models, because I'm assuming they're not fully sealed. Or if we're doing a full curtain wall, then at least I can assume a lower value. So this is where the dynamic simulations, we start to factor in direct radiation from the sun. We start to see daylight coming into spaces that you couldn't imagine, and it would be very hard to calculate. So these are some of, just a quick chart. We could produce data on basically anything. This chart is, the red is a heating load during winter, and then the blue is the cooling load during summer. And so you can almost see where April and the shoulder months are. You got September and October where it kind of dips down. But this is the data that some modeling softwares can do. Some can output, I mean, most of them output this type of stuff. But where we can take things further is to start to isolate this data. I'm working with engineers to downsize and optimize their mechanical systems. And trying to convince an engineer that their calculations are wrong, that you can actually downsize even more, is hard. I mean, it's a tough job because they got their liability on the line. They need to satisfy thermal comfort, and they don't want to go from a 10-ton to an 8-ton unless I can prove it. But if I can start to isolate your latent loads from your people and say that load is going to go to the energy recovery wheel, which is going to save you energy, which is going to preheat your system, which allows you to downsize your system, it starts to account where, okay, this is direct radiation sun. This only happens at this time. We can minimize it. So we can take this information and design better systems from it. But we need to be able to understand what we're working with and how to apply it. How do we make this relevant? And so sometimes it's a guessing game. And I try to ask them what they want from me. And it's kind of having this dialogue, I think, with an energy model is you tell them what you want and they'll try to get it for you. Because it is tough to kind of, it's like pulling a needle in a haystack. What do you want from me? Because I've got hundreds of thousands of lines of data I can isolate or filter or sort. So, in this data we can translate it in any way that we want. Carbon emissions, we can factor in renewable energy, and now and this is kind of my world. I see these charts, these lines, and these patterns, and these trends, and to me, energy is money. Energy has a variable, it has a time of use. And now when I reduce energy, I reduce cost, I optimize cost. I can start to attach incentive programs to this. So the cost of a kilowatt doesn't actually cost 10 cents. It actually triggers incentives, which actually in Ontario, thankfully, you've got lots of incentives. So you can start to calculate and add all these more formulas that makes the whole process really fun. So here we've got solar. So there's multiple modules to energy modeling, and this is where it gets really powerful, is that you can actually factor in all these different modules to actually reduce your load. And again, keep in mind, I'm using BIM as a kind of, as a glue to hold it all together. So here's a, 12-story tower in Edmonton that we wanted to cover the whole backside in solar panels. We want to know how much energy production you're going to get, how much coverage. We wanted to passively light the floor space. But as an engineer, again, you don't want, I mean, I work a lot with architects and both engineers, and I find I've been translating the data. The architects want to see the pretty graph that shows you how much light you're going to get, but the engineer wants to know how many lux you're getting at a certain spot. And so you can start to calculate the start of this data. And when you're putting in LED lighting, it's not just satisfying your lighting demand, it's actually reducing your heating load, which then comes back to your mechanical system. So spending a little bit more on lighting might seem like a higher capital cost, but it's actually less. It's actually the opposite, because you can actually downsize other systems, another process. So it's kind of this whole kind of integrated workflow that needs to happen. And now airflow. So again, airflow, not very common up here, but we can start to bring all this data in about natural ventilation. Night flushing is getting very common. Atrium design, optimizing atrium designs, because sometimes we're just blasting a bunch of air in atriums, or we don't have to. We can, and I mean, what the purpose of natural ventilation ultimately is just to reduce summertime cooling peak load. That's ultimately what it is. And again, figuring out the capital viability of these systems, of these mixed mode systems, is that, if you've got, up here we probably have, 800 hours of cooling load. If I can say I can shave off 100 or 200, it might not be viable, might not go with it. If you got a project a little more down south, and I can say I can reduce, out of your 2,000 loads or 2,000 hours, I can reduce 1,000. That's half your cooling load for a passive system. That doesn't cost you anything. You just got to design it properly. You got to make your spaces not so deep, or you got to, account a little bit more fan power, but you got to work with it. But if it's worth going down that avenue, you can start to simulate and analyze these systems and then further reduce them. So this is actually a picture of a chilled beam. And just kind of, engineers like to know that their systems are actually going to operate the way they're supposed to. The thermal comfort will be met. So it's something that we need to have, this engineering grade data. And this is where I didn't find it in the BIM world. So I went and found it in the energy modeling world. And now I'm trying to put them two together. So inevitably, I think we're all it's all going to get there. We're just not there yet. But in the meantime, I'm trying to make it work. So, and this is where it all begins. So the interoperability. And this is the notion of what I created this business on. And it's what David was speaking at, or what he was finished at, was that it's very hard. It's an artwork. But if you really want to, I guess, build something, it's going to work. And now I can actually sit here and say that I perfected the workflow. I've created files. I use GBXML to translate from Revit to IES. And I've created some files that actually don't need any rework. They're just a perfect translation. So now I start to, I teach Revit, and then I can almost teach Revit again in a way that I translate files. So I draw analytically now. So I draw in a way that, what does my translation files need, and what do they want? And once you can figure out what they want, and this is not something you can look up on those forums, it's just kind of learning through errors. It's learning through doing. And so when I do these exchange files, I figure out all my errors, and I figure, okay, how do I solve this error? Oh, I did this, modeled this wrong, or I modeled it. There's no right and wrong. It's just a matter of, what does the software want from me? So, at the end of the day, it's the software's responsibility to take on, fix all these problems. In the meantime, I'm just the end user trying to make a living and trying to clean up my models so that it works. So there's a lot of tricks. The list can go on. I can have a whole list of bullets up here of what you should do. But basically, in a general sense, you've got simplified enclosures. So I keep things very simple. I keep things, the room bounding elements, sometimes they mess things up. So things like columns. Complete all the volumes. If your wall doesn't go all the way up to the roof, that's going to make a hole, clearly. And not everything translates. So I create files up to the point of what I need and nothing more, because my U values, I know with GBXML doesn't translate. So that I have to go back in to IES and update those. So there's no point in for me putting that into Revit, because I'll have to update it anyways. Things like windows can be a little tricky. So it's been a kind of learning process, but I want to say that there is a lot of hope that it can be done. I've seen some other firms out in New York have done this. So this is picking on in the meantime. And John, I've tried IFC. I tried the integration. It doesn't work for me. So it's not there yet. So it's something that IFC, it's on my radar, but I can't make it work. So if I can't make it work, it's a write-off. Come back to it next year when next phase comes out. So it's something that, as for analytical softwares, it's not there yet. The GBXML import is definitely the key right now. And this comes to my inputs and outputs. This could be very boring or very interesting. To you guys, it's something that things get more rich. And so this is my communication slide. This is where, as an energy modeler, I got to go through all the lighting loads for the entire building and all the heat gain. I have to go through everything in a very fine grain. And to me, as I started off with BIM, it's not hard for me to draw in CAD or to draw in BIM. It's the same level of work. So I figured, why not start putting this data back in? And so I start to enrich models, and I start to build this data so that you guys can now use it. Things like the diffusers now have airflow. Your light bulbs have a power factor. Your window has a performance, because I've got to go through this stuff anyways. And I'm building these components up, and I'm building Revit models. It's not in my scope, but really it's easier for me to do it that way, because I've got a database that's organized. I've got Excel spreadsheets to work with. So to me, it's fine. It's not anything harder to do, and that's what I think is getting easier and easier, because I've simplified my process. I've been actually working on trying to improve quality, and so this is where I got more efficient at things. So I started just spending my time on quality and see how I can make a better job. So I'm sure you're all kind of aware of the standard, I guess, file in Revit, but these files now are used to have just default data or nothing, or it wouldn't be relevant. But to an engineer, we can start to build all this data in. So I don't have to talk to you guys about clash detection, but it's the inevitable next step. Once all the systems are in, once they're all placed, then we can start to do a clash detection check. It's the byproduct of what we do, but I don't have to tell you guys. And then the schedule simulation. Again, we can start to make things modular, and there's a greater cost savings to this. And so these are prefab mechanical services, and it's one thing that I'm out in Alberta, and it's very different out there. It's very driven by builders, developers, and what I'm trying to hopefully change is that these developers, they're after their bottom line, which is fine. I'm hopefully trying to change that by saying, okay, if we save you money with BIM, if we save you time, off your schedule, theoretically we saved you money. If we're still in the design process, why can't we just reinvest that money into more energy conservation measures? So what I created here is we've got construction costs at the bottom, we've got annual operations on the left. So this is a very simple concept. You spend more money on energy conservation, you reduce your operational cost. But basically the black line in the middle is your budget. You can't, you can't make a bigger budget. You've got to work with what you've got. And that's fine. I respect the budget, and I try to work with it. But if we can start to say, okay, we just shaved off 6 weeks off your schedule, which saved you X amount. Now, what if we apply X to more energy conservation measures to actually increase your performance on your building? We can actually, put those triple pane windows that actually, gives you a 10-year return all the way down to a 5. Wouldn't the builder just kind of love that? So I'm kind of trying to use these analytical tools to do cost optimization. And like I said, energy is money. And so if I can use these variables and apply these same concepts to them, I think there's a lot that's going to change. Because I'm just trying to create a green building. That's the main reason why I started working in this world, because I just want to do this type of work. But there's a lot of barriers. And after a while, after a while of getting beat down by all the developers, you got to find a solution to this problem, and I got to give them what they want. So, so that's my thing about the cost. Compliance, I don't want to talk too much about compliance, but basically we've got, you know, the Ontario Building Code that now has upped their game. You've got to be, if you got a 40% glazing building, you got to be beat ASHRAE by 5%. I don't think they have the resources to check all those energy models, but so ASHRAE 90.1, 2010, things are getting tougher and tougher. I mean, if you want to, it's getting harder and harder to meet these compliance reports, and this is where you know, LEED has been a big driver of what we do. It's been pushing the boundaries. It's been allowing you, you know, you want to LEED Platinum, you need an energy modeler. And I'm not trying to sell myself, but you need 15 points that the energy model is going to spit out. And again, here you've got the HP&C program, which pays you per kilowatt that you save. So to me, the more kilowatts I can quantify, the more money you're going to get. And this is a problem with using things like EU4. And actually, the problem with the HP&C program is that, like David was saying, they don't like my models. They don't understand them, and they send them back. So I've got to go and build a compliance report, and I've got to build an EU4 model to comply with them. But my EU4 model doesn't factor in heat recovery. I mean, the building envelopes aren't as good, and I'm coming out with a worse performance, which gives you a worse return, which less incentives. But I mean, so anyways, that's kind of part of the problem of kind of being ahead, is that, you know, I'm a little too far ahead, that they're trying to set me back. And so the software is very complicated, but you know, I'm in discussion with them to try to change that, but it hasn't gone anywhere yet. So, and again, with LEED, I'm not a LEED coordinator, but I try to, these are all the LEED points that I can automate. So these are all the ones that I'm willing to touch, because I can actually automate these points. I can create reports very quickly, very effectively, and these are the ones that you'd want from an energy modeler. So you got the daylight credit, the increased ventilation, green power, renewable energy. Basically, you could just work that in and then spit it back out. So it's very quick, very easy, and it's been driving much of the work. I mean, most of the projects I've worked on are all LEED Platinum or LEED projects. But there's a lot of opportunities. So on the right, you've got the ZEPI score, Zero Energy Performance Index. And what that is basically a chart that is setting the mark on net zero design, and we're trying to get there. And you can see how, I don't know if it's hard to see, ASHRAE 90.1 is that one right at the 50 mark. You can see how the codes are getting harder and harder. We're getting tougher. So they're up in their game, and I know you guys have to keep up. If you want to kind of aim further ahead, you've got ASHRAE 189.1 for high performance green buildings. So that's kind of another step that we can use to kind of aim further. But again, there's not really much for building net zero. There's no guideline, there's no rules. I mean, it's a technical challenge, which is, to me, it's kind of fun. We've got ComNet, which is coming up. It's a standardized energy modeling guidelines. You know, good luck with them trying to standardize that process. But it's something that it's a tough thing to solve. And you know, I'm just kind of excited to see this whole kind of realm develop, because it is underdeveloped. But I think with everything going on with BIM and these softwares, they're moving fast, and I'm just trying to keep up with them. So I want to finish off on this kind of concept of where I started and where I think we're going. So the term big data is kind of like the term, like, you know how the cloud popped up 3 years ago? It just became mainstream. Now the new kind of term I'm seeing is big data and how to use it. So it's kind of like analytics. A lot of the firms use it, like Google, Yahoo, I mean the web-based firms, where they're getting lots and lots of data. And I'm kind of jealous. I want some of that stuff for our industry, and there's no such thing. So I'm kind of, you know, doing a lot of research about this, and what I've kind of get to is on any given day, I can produce over 100,000 lines of data. You know, it's not the Google amounts of data, but to me that's a lot of stuff, and I can barely understand it without these charts, without these graphs, without these images. And so what I'm trying to get to is my workflow is shifting towards a more analytical process. I'm now shifting, associating components with performance, and I'm shifting from these building performance, and I'm comparing one building to another, multiple buildings together, cities to cities. I mean, it's getting to this data world from the smallest micro level all the way up to the macro, and I think right now we've been working towards. I mean, at the top we've got basically the computers. And I'm at the part where I've got a high-powered PC. It's a big, strong computer, costs a lot. But the world that is shifting is getting to a lot of centralized computers, a lot of high-powered computers, things that are all web-based, that are automated. And we've been kind of driving our designs for compliance. So LEED is great, it's driving a lot of stuff, but it's kind of, okay, let's just meet LEED. Let's just comply with LEED. And we're never kind of, so my crosshairs are on zero energy design. How do we get there? So we got to want to be there and then work our way back. And this is where, 3D models can give you LEED, but BIM can give you zero energy design. And it's that kind of that tool to really, to keep driving, to keep pushing further, and to kind of grab all the information and pull it back. So anyways, I've written a blog post about it, and it's a discussion that I'm actively working on this concept, and it's growing again, just like the business I started. It's taking on a life of its own. Data is multiplying every day. So that's all for me. Any questions?
Thanks. Just curious, have you looked at the Green Building Studio technology and what you think of that?
I have. Green Building Studio is a conceptual tool. It works great for what it is. I think it's very good conceptually for architects to be able to run multiple masses, but it stops there. It's only a massing tool, and this is where, I mean, as an energy modeler, I need to go all the way to compliance, and it's not a compliance-driven tool, although it is very, again, it works off the cloud. So if I create 12 masses, I can send them all off, and then we can pick the best one. But then to be able to create variations of those models gets very difficult, because it only produces kind of rudimentary data. So it produces data that, big deal. How do I actually optimize that atrium? Or if that's a full glass atrium, how do I make it more efficient at the conceptual level? So it gives you insight. It kind of points you in the right direction. And it's something that it's available to the architects to kind of start off with. So it's good to get started, but to get the job done, you got to go further, and it kind of stops there.